Hello, everybody. Welcome to the third session of your PyCon 2015. Hope you're having a good morning so far. We are about to listen to Cory Benfield, who is a software engineer at Metaswitch, and perhaps most importantly, a core contributor to Requests library. Thank you, Cory. Cory is going to be talking to us today about HTTP2 and Python. Take it away.
Beautiful. Thank you. Hello, everyone. Kind of hoping my slides are going to show up at some point. Yeah, awesome. All right. Hi, my name's Cory. You have all foolishly decided to listen to me talk about HTTP2 for 25 minutes. It was a terrible decision, and I'm going to punish you for it. I do have a warning, though. I have a ton of material, and I talk quite quickly anyway, so you should shout if you need me to go slower. I apologize to whoever's doing the closed captioning, because I'm going to make your life very difficult indeed. I do want your questions. I'd love to hear them, but because of how much material I have, I might not have time at the end. I'm aiming to have time. Please do keep them for the end, and if I don't have time for yours, come find me or look me on Twitter or GitHub. There's email addresses and stuff all over the place. I'm happy to talk. So as Gabriel said, in my day job, I work for a company called Metaswitch Networks. I mostly work on Project Calico, which is a project for building data center networks, big open source project, a lot of Python code, all about massive scale networking. It's great fun. I'd love to talk about that too if anyone's interested. Again, come find me. But in my spare time, I'm pretty heavily involved with HTTP in Python. So I'm a core contributor on the enormously popular Requests project. I'm a core contributor on the URLlib3 project, which is kind of underneath Requests and also enormously popular and widely deployed. I maintain a ton of other projects in and around this space. And outside of Python, I've been heavily involved in the IETF and the standards bodies that spec HTTP and, in particular, HTTP2. So I've been a long-term member of the HTTP BIS working group, which handles all the HTTP specs. And as part of that, I implemented HTTP2. I was one of the earlier implementers of HTTP2. I've had a stack for about a year and a half now. And so that was a feature in the ongoing HTTP2 development process where we implemented and fed back into the spec design. All right, so why are we here? We're here fundamentally because HTTP 1.1, the most successful application layer network protocol ever designed, is old now. It's really quite old, and it's aged very poorly. So HTTP 1.1's been around a very long time, but it was first standardized in 1996, which is very nearly 20 years ago. And the world doesn't look like it did then. So back in 96, your website was usually just one HTML file, more or less, about 600 bytes in size. At least that's what the W3C page was in 1996. That's a far cry from what you have now, where if you go to the New York Times website, it'll be hundreds of resources and megabytes of data that have to be transferred. This is fundamentally a very different space, and HTTP 1.1 wasn't really built for it. And in particular, at the protocol level, it's very inefficient in that use case. It uses TCP really very poorly. So without going into too much TCP detail for people who don't know about it, but TCP works best if you keep your connections alive and keep sending data down them. TCP is all about adapting to the state of the network. And HTTP more or less doesn't do that. By and large, it doesn't reuse connections. In principle, it could, but there are enough implementation problems that mostly it doesn't. And that means that to retrieve large numbers of objects, like you need to do in the modern web, it requires a ton of concurrent connections, none of which work very well with TCP. They get in each other's way, they affect each other's congestion control algorithms, everything kind of falls apart. Additionally, because we have to keep establishing and tearing down these connections, the latency on these connections can often be quite high. So you need to do a single network round trip just to set a TCP connection up. That can already be hundreds of milliseconds, depending on who you're talking to. Then you might have to do a TLS handshake as well, and that adds another couple round trips. And that's before you've sent any of your web page at all. This is a real problem for HTTP, and in particular, it leads to difficulties for websites that care a lot about speed, and it causes problems for the real-time web, this idea of a web that's kind of live and fast and constantly updating. Your web apps can never be as good as a native app, because your native app can respond in 1 or 2 milliseconds, and your web app has a 200 millisecond round trip. Extremely problematic. So fundamentally, HTTP 1.1 is a limiting factor on the web, which it wasn't when it was originally implemented. Web developers keep coming up with ways to get around HTTP 1.1's problems. Some of these things, just reeling off a list of examples, spriting. So when you've got lots of like icons on one page, rather than have them all as separate icon images, they all go into this one big image, and then you say, I'd like to just display this little section, please. Sometimes that's not good enough either. So once you've done that, you then inline that image. So you base64 encode it into text and then put it in your CSS file where it clearly does not belong, so that you don't have to do an extra hop to get it. And then sometimes that's not enough either. So you take your 15 CSS files, which you had separate because you modularize, because you're a good programmer, and you put them all into one big file and then minify that big file when you deploy to production. And all of this is a desperate attempt to reduce the number of round trips, but you end up fighting against one of HTTP's other great strengths, which is caching. Caching is all about making sure you only request the data that's changed. And of course, now if I change 1 byte of my CSS file, I need to download all 15 CSS files and 200 sprite images all over again, because my cache can't tell the difference. And that's just extremely unfortunate. So basically, it had become apparent to a large number of people that the web really needed an update. And that update came in the form of HTTP2. So I'm not going to talk too much about exactly how we got here, partly because it's a very long story, partly because it's a very sad story, and I'm trying to keep the mood up, and mostly because fundamentally, it's not that interesting a technical discussion. It's a very interesting political discussion. I'm happy to have it, but I'm not going to have it on this stage. So let's talk about what it is instead. The biggest thing about HTTP2, its biggest difference from HTTP 1.1, is that it is a binary protocol. So anyone in the room, actually, can I get hands? Who in the room has actually seen an HTTP message kind of in its textual form? All right, so substantially more than half, more than 3/4, I think. For those of you who haven't, it looks like words. It says get, and then it says the path you want to get, and then it says HTTP 1.1, and then it says some stuff like, I will accept JSON, please, or I am Mozilla. And this is gone. This is gone in HTTP2. It's all binary. So it's instead made of a series of binary frames, one after another, that say, these 5 bytes are headers, these 15 bytes are body, this byte says you can send me 15 more bytes of body, please. Stuff like that. You can't read it anymore. This has caused outrage beyond belief. It's mind-boggling. Text protocols are really popular because they're super easy to investigate with really simple tools. So a killer demonstration used to be you could open up Telnet, which is just a plain it sends bytes one another, and write your little HTTP message to Google, and Google would talk to you. And you got to show off in front of your friends. Well, not in front of your friends, or really show off, but it was a thing you could do. You could do it. And you can't do that now. But the reason for it, and the reason for moving away, is that text protocols are really tricky to parse. So working out where things start and end is really hard. And I guarantee to you that there are plenty of people in this room who think they could write a compliant HTTP 1.1 parser, and almost all of them are wrong. And that includes me. I have written an HTTP 1.1 parser, and I guarantee it's not standards compliant. It's really tricky. And when you make simple mistakes, they lead to really difficult to predict outcomes. You should go to the Python standard library bug tracker and look through HTTP-lib bugs. And you'll find there are many of them that are fundamentally caused by errors in parsing, and they lead to really weird edge case behaviors like permanent forever hangs in your code. They're really quite scary. As a separate one, for people who write embedded code, it's really hard to work out how much resources you should commit to parsing a message, right? Or even non-embedded code, even if you write it in C, which you shouldn't, but if you did, you need to allocate a buffer to store your header, and you don't know how big it's going to be. You can't know. You just have to keep reading data till you get to the end or till you give up. It's really tricky. Binary protocols, on the other hand, are less ambiguous, they're faster to parse, and they consume fewer resources than their textual cousins. From almost every perspective, they are better, except that you can't read them when they pass over the wire. And the big killer advantage of this is you get a simple protocol stack. And because it's simple, it's easier to debug, and it's much, much faster. You no longer need to touch every byte of the message, checking if it's a new line character. And this is the thing to know about HTTP2 if you come away with nothing else. HTTP2 is at its core a binary framing layer for HTTP. It adds no new semantics. You can't do new things with it. All you do is you wrap up your message that means the same thing in just a different wire format. You can translate from one to the other. But we did add some other things while we were there. So we added features all around efficiency, all around trying to send less data, trying to use resources more effectively. The big one is multiplexing. So no longer do you need to open a TCP connection for every request. Instead, one TCP connection may carry many concurrent requests and responses. A well-functioning HTTP2 stack will frequently be uploading 3 separate files and downloading 5 all at the same time on the same TCP connection, interleaving their data. Here's another thing to know if you're going to work with this. The most useful new term coming out of HTTP2, a single request-response pair is called a stream, and it has a stream ID. You will start seeing these when you debug now. You'll say, oh, what happened to stream 56? Worth bearing in mind that term. Multiplexing is not good enough, though, because if you just plain multiplex, you block. You'll do head-of-line blocking, or you'll send data you don't need. So we also added priorities and flow control. Priorities basically mean that each stream tells you how important it is and what else it depends on. So you can make sure you apportion your resources appropriately. Flow control also makes sure that you only send data as fast as the other end can handle it. There's no point sending data faster than the other end is doing anything with it. You're wasting your time, and you may as well spend your resources elsewhere. These are both extremely useful. We added header compression. Anyone who's looked at an HTTP 1.1 header block knows that it's frequently larger than the message it transmits. It's hundreds of bytes. It's crazy large. So we wanted to make them smaller. Now, one way of doing that would be to use something like gzips, some kind of static text compression, and that works. But it's not perfect, because the real way to make headers smaller is to optimize their structured data, and you can take advantage of that. So we did what every sane group of people would do and invented a new header compression method. It's called HPAC. And it's designed expressly for HTTP headers. So that means it can say things like, please resend this header that I sent you previously. That takes 1 byte. So you send your user agent string once at the start of your session, and then forever it's just, and send header 1, please. Saves tons of bytes. It's great. It also includes some privacy features. So it says things like, please never compress this header. And that's really useful, for example, for passwords. Which you absolutely do not want to compress, or you get things like breach and crime and all kinds of attacks on your TLS session, and then everyone gets really sad and has terrible talks, like some of the other ones going on about how TLS is terrible, but it's all our fault, and it's just bad. You can abort your requests and responses without losing the connection, which is super valuable, because obviously you've spent all this time building up your TCP flow control windows and establishing your header compression state. You don't want to throw that away just because you asked for a 15 gigabyte movie file you no longer want. So you can just send a very short message that says, I don't need this anymore. And that's particularly useful with server push. So server push is kind of the biggest headline feature, although it's not actually that widely used, and it probably won't be. But the server can send you responses to requests it thinks you will make. And this is not some form of psychic wizardry. It's to do with things like the server knows that this HTML page calls in these 5 JavaScript documents, and so you're almost certainly going to ask for them, so it will send its response in advance. This is only for priming caches. That's its whole purpose in life, is to make sure you've got your cache ready so you can just serve the response out of the cache. If you don't want it, you can abort it. Why would you not want it? Is a key question, and the obvious answer is, in order to send a response, you need to have made a request, but you didn't ask. So the server will actually send you the request it thinks you will have made in addition to the response to that hypothetical request. And so you might discover that that request looks nothing like what you were actually going to send, and so you need to cancel that and send your own. It's quite important. All right, so here's the thing. HTTP2 has not been received as the second coming of the world's most popular protocol. Unfortunately. There was a lot of criticism of HTTP2. I'm calling out one bit in particular, just because I'm quite certain a lot of people in the room will have read Paul Henning-Kamp's various documents taking shots at the protocol. Paul Henning-Kamp, for those who don't know, he's a BSD developer. He's the lead developer of the Varnish HTTP cache protocol, and he's circulated a lot of writing about how terrible HTTP2 is, and I myself am very glad that he doesn't have a protocol design class for me to flunk out of. But the question is, why? Why is there so much negativity about HTTP2 when it's got so many nice things in it? And the real answer is because much like HTTP 1.1, it's a flawed protocol. It's not perfect. I would contend that no protocol ever is. And so we've traded some downsides for other downsides. Some good examples. It's really tricky to reason about. So HTTP 1.1 has as one of its great joys, it is very easy to look at a request and spot what the problem is. So human brain is great at pattern matching, and we can look at this text response and go, well, that can't possibly be right, because weird thing here is going wrong. And it's hard for code to spot that. But the worst part is HTTP2 maintains really extensive state in its connections. So in HTTP 1.1, you could hop in to the 5th request in a sequence, and it was standalone. You could understand it in its complete context with no extra tools. And you can't do that in HTTP 2, because you've got header compression state. So your 5th request will say, and now resend header 5. What the hell was header 5? I have no idea what header 5 was. So you need cooperation from your tools. And this means that basically tools now need to be able to drop their connection state into debug logs for you to successfully debug. And most tools have not written that function. This also means that it's really hard to debug. You need to do a ton of interop testing. That's just the only way you can be sure that you've implemented this correctly, is to go get every other implementation and run your code against them. There are some great resources for doing this, but you do have to go find them. It's got some really terrible, awkward edge cases, and these came out because we were required to maintain compatibility with HTTP 1.1. So anything you could send in 1.1 had to be sendable in HTTP 2. The biggest problem for this is headers. So HTTP 2 frames are they have a maximum possible length. In practice, it's about 16 kilobytes. And it turns out that you can have a single header that is more than 16 kilobytes long. Kerberos will frequently is a bit strong, Kerberos will generate headers that are that large for their tokenization. Now, for me, I would call that a good reason to abandon Kerberos, but unfortunately, I can't make those mandates, so instead, we have to allow it. And this means, in practice, you can freeze an HTTP2 connection dead by sending sufficiently large headers and not finishing them off. This is really quite tricky. A fun one for Python, though, is that fundamentally, HTTP2 is inherently concurrent. It's got one TCP stream down which it sends data and also control frames. So things like, is this connection still alive? Please increase your flow control window. Please change your header compression state. You need to process these promptly. You need to be pumping that connection all the time. And this is really difficult in synchronous programming, like what a lot of us do in Python. If you're used to using requests, you're going to find this really very tricky. And we've got to do a lot of clever work to make sure that we can handle this appropriately. It's going to be really hard. I'm probably not smart enough to solve it. If there is anyone, please come talk to me, or even if you're not smart enough to solve it but would like to help, I don't think I can do it on my own. Fundamentally, I wouldn't be at all surprised to find that HTTP2 is the primary motivator behind a big pickup of async I/O. And for those of you who haven't used async I/O and aren't familiar with it, Nicholas Tollovy is talking about it. He's doing an introduction to async I/O. I recommend going, because if you work with the web, you're probably going to want to start using it. But despite all of these things, in a lot of cases, HTTP2 is really good. And as an example of how good, I want to bring up this. So this is from the Go programming language's HTTP2 webpage. This is their gopher tiles demonstration. You can load this up now. If you Google gopher tiles, you can find this for those of you who have laptops in front of you. So each of these images is made up of 180 tiled smaller images. The one on the left is being served over HTTP 1.1. The one on the right is being served over HTTP 2. These are both from Chrome. So if you've got Chrome or Firefox, HTTP2 works right now. You can literally test this while I go. So I'm going to start them both at the same time. And by at the same time, I mean I'm going to give HTTP 1.1 a second of head start. And we'll see which loads first. Oh, well, that was easy. And this is consistently true. So there's lots of great, you can't really see there because I compressed the hell out of these images. But there's a ton of various options. You can add latency to the requests, for example. So that was the zero latency demo. That was the best case for HTTP 1.1. And HTTP2 smokes it out of the water. And that's consistently true. I tested this with my HTTP2 implementation in Python. And I could, The only way I could get HTTP 1.1 to be as fast was to start 180 concurrent connections. So I had to download them all in parallel at the same time. That does not scale to everyone on the internet doing that. So HTTP 2 has got some serious advantages. Right, so it's really good. How do you get to play around with it? So there are at least 34 current implementations of HTTP 2. This is not all of them. This is a small list. They've got various exciting names. Some ones on this list that are worth flagging up. There is Hyper, which is a Python client library. I'm going to talk about that in a second, because it's mine, and therefore worthy of your time. There's ng-HTTP2. ng-HTTP2 is kind of the open source reference implementation for HTTP2. It does all the things. It's a client, it's a server, it's a proxy, whatever you want it to do. Its only downside is that it's a nightmare to compile. It has a lot of dependencies, but if you can interop with that, you can probably interop with a lot of other tools. Firefox and Chrome both have implementations. They're using it today. If you go to Twitter on one of those, you are probably using HTTP2, because Twitter have an implementation as well. Wireshark can decode HTTP2 frames, which would be really useful except for the fact that HTTP2 is almost always served over TLS. Curl and libcurl can do HTTP2. They use ng-HTTP2's stuff, so you need ng-HTTP2 first, but then you can use HTTP2 with curl straight out of the box. Internet Explorer is working on one, for those of you who love Microsoft. And there are plenty of others floating around for your favorite languages. In fact, Python is one of the languages that is underserved by implementations. There are more implementations for Haskell than there are for Python. So let's talk about Hyper quickly then, Python's current only HTTP2 implementation. And it's not even a full implementation. It really is just a client library, because that's really all I care about. So Hyper fits in roughly the same place in the HTTP stack as HTTPlib or HTTP.client. And if you've never used either of those directly, then probably it's the kind of thing you're not going to want to think about too much. Its real goal is to slot in at the bottom of the stack, roughly where they do, so that we can put URLlib3 on top of that, and then requests on top of that. It is still under very active development, but it's primarily just me. I get a lot of people kind of floating in and out to contribute, but I don't have a lot of people working on it consistently who aren't me. It's got a lot of feature requests open. It's got a lot of issues open. Help would be good. But you can find it there on GitHub if you want to look at the code. Some of the code is good, some of it's terrible. And you can get docs. So if you just want to play with it, if you just want to try stuff out, you can go to the documentation, you can download it from PyPI, and you can just start making some requests. One place you could try making requests to is HTTP2 bin. So this is HTTP bin, which plenty of people will know about. It was originally developed by Kenneth Reitz and is now maintained by the lovely people at Runscope. And it's exactly that, code for code, exactly the same. It even identifies itself as HTTP bin. But it's running behind H2O, which is an HTTP 1.1 and 2 reverse proxy. So it can speak HTTP 1.1 and HTTP 2. I've got Dockerized versions of all of these, so you can go to my GitHub and pull them down in Docker containers and just go. I haven't uploaded them to Docker Hub yet, but I will do. So you can deploy them internally if you don't trust me to store the data that I don't get from this service. The other thing to know here is that H2O reverse proxies to HTTP 1.1, so you can put it in front of any Python web app you have right now and give HTTP2 a shot on your app, just to see how it feels. So if this is something you've got, if you've got stuff floating around, I highly recommend giving it some time. Take a look at the Docker file to see how that sort of thing works. If you want to do more reading, if you're interested, you want to see more, then there are two major resources. The top one is from the curl developer, and it's an enormous document that covers the why and the how and the what of HTTP2. It is the resource. If you take nothing else away, that URL is great. Then the page one down is the HTTP business card page, and it contains the specs and links to implementations and all sorts of other stuff. All right, so that's pretty much my time. I will be happy to stop for questions. I'm going to make one quick note. The requests core team are going to be at the NUM Focus booth tomorrow from 12:30ish. If you want to come chat to us, have lunch with us, we'd love to meet you. We just want to talk about anything with people who are using our stuff, get your feedback. But that's all from me. Thank you very much.
Great. We have a few minutes for questions. So if anyone has any questions and would like to come to the mic back here, we will take them.
Okay. Hey, awesome talk. Thank you very much. I had two related questions. The first one is, so let's say if you are running a website and running web servers, like what are the options to support HTTP2? So you mentioned that reverse proxy, but like what about native implementations if you're running Apache, Nginx, whatever else?
Right, so the open source web servers are moving relatively slowly. Nginx have said they'll have support by, quote unquote, the end of the year, which is thoroughly disappointing. So hopefully someone will step up and make that happen faster. Apache's getting there. There is a mod H2, that's what it's called, it's mod H2. I don't recall how far through development it is, but that's the thing to look at. It's also built on top of ng HTTP2.
Okay, and the next question kind of related to that, like, when do you expect, in terms of adoption, we'll see like the whole internet running on HTTP2 and people kind of talk about 1.1 being like this back in the day sort of thing?
I'm not certain that we will ever totally get rid of HTTP 1.1. There are a few use cases where it's a little bit better than 2.
In terms of like, wide stream adoption, it's
yeah.
like the more mainstream thing.
So mainstream adoption, I think within this calendar year is the answer. So it is already more widely used than IPv6 is. And it's not actually even fully standardized yet. It's still in the IESG, so it's still got a bit of work. But so Google have deployed it already. So Google and Chrome, anyone using that is using it. Twitter again, there are lots of big websites that are deploying it really fast. I suspect Facebook will be along soon as well. Lots of the big social media stuff will. So I'm confident this year.
Awesome. Thank you very much.
Thank you.
My question concerns the push features that you briefly mentioned. How do you see this working with popular web framework? Is it like you're going to declare what needs to be pushed on each page? Like, yeah.
Yeah, I think popular web frameworks are going to need extensions to try and work this out. That said, I would think it would be not too challenging to add a reverse proxy that uses some machine learning stuff to try and work out what requests correlate together in such a way that it could do quite well. I'll probably try and have a conversation with the H2O lead at some point about whether or not we can try it with his implementation. Yeah.
Will you be working on Hyper in the sprints?
I think I'll be trying to do some, yeah. I'll be here Monday. That's the only day of the sprints I'll be here. But I'm certainly happy to talk about ramping people up on it so that other people can sprint on it if I don't have the chance to.
Thanks.
Yeah, request response pairs are called streams when they're multiplex. How does the prioritization and flow control interact with TCP's prioritization and flow control, and even IP's facilities? It seems there's some redundancy there, maybe some potential for fighting between those mechanisms.
So the goal should be that they won't fight. So the key thing to know, and this gets brought up a lot, and there's some discussions on the mailing list about it, which might be worth trying to find with some Google, but the kind of high-level stuff here is the flow control is application layer flow control. So it's about whether or not the application itself is processing the data. The TCP stream should still be being pumped because you need to get those control frames. So TCP's flow control is an orthogonal thing, which is saying the server as a whole cannot process more data. Not this particular instance of this web app cannot process more data for this stream. So it's a much more fine-grained issue. There should be, with carefully tuned algorithms, no head-of-line blocking. However, you can definitely do it wrong, and it's an important thing that has to get tested live.
That's kind of what I'm asking. Has there been much testing or investigation into how those interact? There's so many flow control algorithms for TCP because of the same issue between IP layer stuff.
So there's definitely less work done than TCP, but there's plenty of implementations floating around, and for a little while we had a special frame that would tell you if you had blocked a stream that could be served for some debugging purpose. It got taken out because it added some complexity, but the thing to do is to go to the various major implementations and ask them to kind of write a document that tracks exactly how their algorithms work, because they'll all be quite different. I suspect Google will also publish a white paper.
Thank you. Great talk.
Thank you.
Hey, thanks for the talk. I had a question. So HTTP2 makes a lot of sense between the browser and the web server. What do you think its place is within the architecture? If you have microservices talking to each other, do you think it has a place there? Maybe without TLS? Or?
I think it has the potential to be extremely valuable in those cases. It's a bit interesting because it very much depends on your network topology. But in principle, it has the ability to be a really great kind of RPC mechanism. And in fact, there is one already. Google have published gRPC, which is an RPC mechanism over HTTP2 using their various Go implementations of it. And that has the potential to be much, much more effective than the current HTTP 1.1 use of that.
Thank you.
Thank you.
Is a given page or session typically restricted to a single TCP connection? And if so, is that a bottleneck, or do you ever foresee that being a bottleneck in the future?
So the spec says that there should, capital should, be no more than one TCP connection per authority, so host. So yeah, in principle, I should maintain only the one connection to a Google server. Currently, we don't expect that to be a bottleneck, but it's the kind of thing that we may well come back and say, well, actually, we need more. Ideally, I think what we'd actually do is reconsider the way we handle the one connection. One connection should be the optimal case for TCP. Hopefully it will.
Okay, thank you.
Thank you.
You mentioned that the binary nature of the protocol makes it easier to parse in resource-constrained environments. Is it possible to disable other features such as HPAC and mandatory TLS to the point where you could actually run this thing on an 8 or 16-bit micro like an Arduino?
Maybe. There have been some people doing work on that. I'm not entirely up to speed on where they are, but you can disable many of the complicated features. So flow control, you can have a kind of no-op flow control algorithm that always just sends back window updates that are exactly the size of the data you received. And in fact, that's what Hyper does right now. Actually, no, it doesn't. I made it smarter recently. It doesn't do that anymore. But you can turn off the compression-y parts of HPAC. So you can have HPAC basically say, you can never add headers to the compression table. And then you just always get essentially uncompressed headers. I don't think you can turn off Huffman encoding for those headers, though. So you may have to do Huffman decoding. I need to check. Should be possible.
Thank you.
Hi. Other than the RPC use case, what do you see Hyper being used as in Python, or used for in Python?
Yeah, that's a good question. I have an explicit long-term goal to get requests to use it. I'm kind of cheating, but the focus there is I would like to be able to transparently interwork between 1.1 and 2 so that you can use whatever is most present. It also has a thoroughly separate framing layer. So the bit that knows about HTTP frames and the bit that knows about HPAC are quite separate and could be broken out into their own libraries quite easily. So I'm talking to someone who is considering adding support to the standard library using the framing layer. I also plan to add support for things like Twisted and G-Event and all those sorts of things. And ideally, I'd like to write a server implementation at some point as well, probably on async I/O. But that's assuming that I have 8 million hours, because there's a lot of work there.
Well, a follow-up to that. Usually, the flow in Python, or I guess in most cases, is a request-response kind of deal.
Yeah.
Where HTTP1 probably works okay. So is it a different interface that request is going to implement, or do you have any vision there?
My expectation is that we will keep that abstraction, but in practice, to get good performance out of it, to get like excellent performance out of it, you will need to start having some concurrency in place. So you might use one of the concurrent interfaces to requests, like G requests or T requests or TREC or any of those, or even just spawn a background thread that in practice all of your things multiplex onto. So you can have many, many threads running, and they all actually use that one underlying connection multiplexing down it. Again, I'd love to talk about this with more users because I want to get a feel for what those use cases look like. It's easy for me to just design in a bubble, and then no one will like it.
Thank you.
Thank you.
I have a quick follow-up question to go after the one about server push. So it seems like HTTP2 is going to require the application layer to be much, much smarter than it is right now with HTTP1. The application layer is going to have to decide what to push ahead of time, what the user is going to need, everything ahead of time. Do you think there's a solution to that in Nginx? Or do you think it's entirely the responsibility of the application developer to make it smart enough to handle HTTP2?
I think with computers, almost everything is possible. So I think that you could absolutely solve this in Nginx. And I think anyone who does is going to have a really great conference speaking career and hopefully turn it into quite a bit of money. But in practice, currently, the application layer has to know about it. So lots of the expected ways of dealing with this will be to add extra headers that your server intercepts that say things like, this other resource is related, please push it. So that's the current expectation of the flow. We'll get that right first and then worry about being smart.
OK, thanks.
Thank
Great
you.
talk.
Thank you.
Hi. I wanted to ask if there's anything on the roadmap for the standards committee to deal with or address some of the shortcomings that you called out?
Currently, no.
Like debuggability.
Yeah, so the answer is currently no. There are a couple of layers to this question. So firstly, the working group is exhausted. HTTP2 was a battle. It was a battle for 2 years. There was a lot of contention about it, a lot of back and forth, and a lot of people just need some time to not do that. Arguments on the mailing lists get tiring after a while. That said, there has been lots of explicit discussion about HTTP3. We're not proposing to do it right now. No one panic. But it's the kind of thing that we're prepared to talk about. We're going to let the standard kind of boil, kind of simmer for 6 months, let people implement, let people find the actual problems they hit in the wild. And then we'll come back to the table, I think, and look at whether or not we can address these with extensions or whether or not we really have to respec. One of the good things that came out of this was a whole infrastructure for transparently adding extra protocols that you can upgrade to. So hopefully, further HTTP versions should be easier to handle than this one was. This one required a lot of extra infrastructure.
Thanks.
Thank you.
Cool. I think we're going to have to cut it off there because I am hungry for lunch. So thank you very much, Cory. And
thanks, everyone.
Lunch, folks.